Good to hear that. Okay, so let's start. Today we are going to resume forces in equilibrium, and we're going to do one component of it, which is called string and tension. So I'll share my screen with you guys. There you go. We're done with kinematics, okay? And remember, you guys have a test. I announced it in the group, so I hope you guys are preparing for it. No, this is not related to connected bodies. Acha, before I start, just a minute. Okay, now, so basically, just to give you guys an idea of the kind of questions that we're going to be dealing with in this component, these are the kind of questions. Okay, so where you have a string and an object is hanging from that string. So there are three possibilities. One is that you have the same string. The other is that you have two different strings, or like for example over here you have two different strings. And there is these are the two most likely possibilities that we're going to be dealing with. Okay, but before we dive into the questions, there are some concepts that we have to cover. That is, we need to first understand the types of forces that we're going to be dealing with. Okay, now we start off with the one very common force that we deal with, and that's called weight. Now weight, what we refer to normally and what weight is, theoretically they're two different things. What do we refer to weight normally? Like, normally what
Mass.
sorry?
So normally we assume that weight is mass.
Yeah, exactly. Normally we assume that weight is mass, whereas they're two different things. You know, like say someone says that I weigh 80 kg. So 80 kg is actually the mass. Okay, weight is the force exerted by gravity on an object by definition. Okay, so weight is calculated using mass and the acceleration due to gravity. Okay, so weight is actually worked out using mass and multiplying it by the acceleration due to gravity. So let's say if somebody weighs 80 kg, as we say weighs 80 kg, that means their mass is 80 kg. So as they walk around, what is the force that they exert on the ground? You know, as they walk around, as someone who weighs 80 kg, as they walk around, what's the force that they're exerting? That is the weight. And how do we figure that out? We figure that out by taking 80 and multiplying it by 10, which is equal to 800 Newton. And yes, we take g, acceleration due to gravity, as 10 meter per second square. Okay, the exact value is 9.81 something, but we round it off and we take it as 10. Okay, now a couple of things to know about weight is that first of all, it always acts downwards from the center of gravity. Okay, so if let's say this is a horizontal ground, okay, or a horizontal plane, sometimes we refer to it as a horizontal plane. So if this is the object, this is the center of gravity of that object, and from this point weight is acting exactly downwards. Okay, so in order to work out the weight of this object, we'll take the mass and multiply it by g, okay, which is acceleration due to gravity. Now you won't always have an object on a horizontal plane. Sometimes you are likely to encounter a question in which the object is on an inclined or a declined plane. In that case, although we're not going to go into the details just yet, okay, we'll go into the details when we're studying inclined and declined plane. But just to give ourselves an idea, just a minute, the pen is not responding. But, sorry. Yeah. So just to give you guys an idea, like I said, we're going to pick this up in detail later on. So let's say this is the horizontal plane, and on this horizontal plane you have an object. Okay, so if you have this object which is on a horizontal plane, where will the weight be acting? So this is this. So this is the center of the object. Okay, and from the center of the object, the weight will be acting downwards. Okay, so this is the direction in which the weight must be acting. Okay, and how will we work out the weight? The weight will be equal to W equals to mg. And then later on we'll see how we break it down into two components. One is parallel to the plane and the other is perpendicular to the plane, but that part comes later. Okay, for now just remember how weight is calculated and the direction in which weight acts. Okay, and that is, it always acts downwards. Then normal contact force. Now in this chapter, we're not going to be dealing with normal contact force very often, but it's still a good idea to understand what it is. So what's normal contact force? It's the force that surfaces exert to prevent solid objects from passing through each other. So for example, let's go back to the horizontal plane. So on this horizontal plane, if you have an object, okay, why is it that this object, although it's exerting a force that's acting downwards, which is its weight, W equals to mg. Why is it that this object does not fall through the table? The reason behind that is very simple. We saw this when we were doing coplanar forces as well. Is because the surface is also exerting an equal amount of force. Okay, and that force is called the normal reaction force, which we refer to as R. Okay, and where do we find this force? We find this force only at the point of contact. Okay, and because this object is not moving up and down, it's safe to say that this is in equilibrium, and that means W equals to R. Now what happens if you have an object on an inclined plane? So if, let's say, this is the plane, and on this plane you have this object. Okay, so now we saw earlier how weight will be acting downwards. Okay, and it's going to be equal to W equals to mg. Now what about the normal reaction force? The normal reaction force, remember, is the force that is always perpendicular to the surface. Okay, normal reaction force is always perpendicular to the surface. So the normal reaction force will be acting in this direction. Why this direction? Because this is perpendicular to the surface on which the object is resting. Okay, now we will not be dealing with these forces right now. We will be dealing with these forces later on, but it's, like I said, it's a good idea to write them down now only. Always acts perpendicular to the surface. Okay, now then we have friction. Again, we're not going to be dealing with friction right now in detail, but still it's a good idea to go over what it is, so that later on when we're doing objects on an inclined plane, we know how to work with friction. So what's friction? I'm sure all of us have some understanding of the word friction, but formally it's the force that resists the sliding or rolling of an object, always acts in the opposite direction of motion. Okay, so once again, if let's say you have an object which is on a horizontal plane, something like this. So this is the plane, and here let's say you have an object. Okay, so if let's say this object is being pulled, okay, if let's say there's a driving force or some force that's causing this object to move, and this object is moving towards the right, in that case, where will friction act? Friction will be the force that's acting in the opposite direction, in the direction opposite to the motion of the object. So this is the direction in which the frictional force must be acting. And then where must the weight be acting? Weight must be acting downwards. What about the normal contact force? Upwards. Okay, and how do you calculate frictional force? The formula to calculate frictional force is mu times R. Okay, more about this in detail later on when we're doing this chapter. Right now we're just writing it down. Mu is a constant which is called coefficient of friction. This is usually given, or maybe we're given enough information to work this out. And R is the reaction force. Reaction force, or as we call it, the normal contact force. Now, if let's say you have an object on an inclined plane, and the object, due to its own weight, ends up sliding down, so where must be the frictional force acting? Question for you guys. So let's say you have an object on an inclined plane, and this object ends up moving down the plane because of its own weight and because of the slope. So where will the frictional force be acting? No, we're not talking about max friction or anything right now. Okay, that's something we will discuss when we're dealing with actual questions. Right now we're just going over the basic concept. Okay, so coming back to my question, if you have an object which is sliding down the plane because of its own weight, sorry,
exactly opposite, like towards
exactly
the right.
opposite, then the frictional force must be acting in this direction. Okay, and remember, this is the weight component, W equals to mg. Now later on we'll learn how to find the component which is horizontal or which is parallel to the plane and perpendicular to the plane. Okay, so a couple of key points here. Number one, if object is sliding down the plane, the frictional force is acting up the plane. Number two, if object is moving up the plane. Now the object won't just naturally start moving up the plane. It may be because of an external force that's being applied. Moving up the plane, the frictional force is acting down the plane. So frictional force, remember, is a kind of a resistive force. Okay. Now, a couple of keywords to keep in mind. If the object uses the word smooth, smooth string, smooth rod, smooth ring, whatever, in that case, smooth plane, in that case there is no friction. Okay. If the object uses the word rough somewhere, rough plane, rough whatever, in that case there means there is friction. Friction exists. Okay. Now, then we have tension. Tension is what we're going to be focusing on today. Okay.
And could we scroll up a bit?
Yeah, sure.
Oh, so thank you.
Okay. So what's tension? Tension is a force that's transmitted through a rope, string, or wire when pulled by acting from opposite sides. And remember, it always acts away from the object. Okay. So if let's say you have a horizontal beam, okay, and from this beam you have a string. So when the surface, Momina, that's not the case. The question will always specify whether it's a smooth surface or a rough surface. Okay. Now, from this beam, let's say you have an object that's hanging. Okay. Acha, a couple of terminologies that you need to know. One is taut and the other is slack. Okay. Now, what does that mean? Taut and slack. Any idea? Let me see if I can give you an example. So let's take this wire for example. Okay, can you guys see my screen? Yeah, my camera, yes. So at the moment, this wire, the way it is right now, it's slack. Okay. Now when I pull it from both sides such that it's not loose anymore, that means it is now taut. Okay. So slack, taut, slack, taut. Okay. Slack means no tension, taut means that yes, there is tension. Okay, taut is basically when you pull it or you hang an object from the end or to a string or a wire, that is how it becomes taut. Okay, so taut is like this, and if it's slack, then that means it's going to be something like this. Okay, Achha. So as I was saying here, if you have an object which is hanging from a wire or from a rope, whatever, okay, from a string, doesn't matter. So in that case, we know that this object, the weight of this object will be acting downwards, W equals to mg. And what about the tension? The tension will be acting away from the object. Okay, and if this is not moving up and down, then it's safe to say that W is equals to the tension. And the reason why we're calling it TA is because this object is what we're referring to as A. Okay, so the weight of A is equals to the tension in the string. Okay, if let's say you have two objects, because normally there's confusion when we have two objects. If let's say you have two objects right here, okay, let's say you have two cards, for example, two cards, and let's say that they are connected by now let's say these two cards are connected by a string. Okay, let's call one card card A, let's call this card A, and let's call this card B. Okay, now where will the tension be acting? So for card A, the tension will be acting in this direction, okay, and for card B, the tension will be acting in this direction. Okay, so remember, it's always opposite to the object. Okay, always opposite to the object. And if let's say it's the same rope, okay, which it is, if they're connected by the same rope, then the tension, the two tensions are going to be equal. TA equals to TB. Okay, that is if it's the same rope. All right, now there is another possibility. So here's case 1, here's case 2, and then there is case 3. Yeah, sure, I can explain this again. So if let's say that you have two cards that are connected, and let's say both of these cards are moving in this direction. Okay, obviously both of them have to be moving in the same direction. It's not possible that one is moving left and the other is moving right. Okay, let's say this is the direction in which they're moving. So that means there is some force that's pulling both of these cards towards the right. Okay, now when we're looking at B, we're only looking at B, we're not looking at A. Okay, so where will be the tension of B acting? It must be acting away from the object. So that's why it's acting towards the left. Okay, and what about the tension of A? This also must be acting away from the object. That means towards the right. Okay, and because it's the same rope, the two tensions must be equal. Okay, more about this later on. All right.
If the object is moving towards the right, why is tension's direction also towards the direction of the motion? Tension A की.
देखो, so basically think about it this way. There is some force that's pulling this. Okay, there is some force that's pulling this. Okay, what is that force, or how is the force being transmitted? The force is being transmitted through this rope. Okay, now what is the direction in which, now remember this, when we're looking at object A, we're only looking at object A, we're not looking at object B. And what's the rule for tension? Tension always acts away from the object. So if you ignore object B for a minute and you just look at object A, where must the tension be acting? Which way is away from the object? Is it towards the right or is it towards the left? If it's towards the left, then what does that mean? That means it's acting towards the object. No, it's got to be acting away from the object. That means it's acting towards the right. Okay, so we look at each object one by one. We don't look at them collectively, we look at each object one by one. When we're looking at B, we're just looking at B. We're not looking at A. So if B is connected, or if B has a rope attached to it, where must the tension be acting? Away from B. So that means towards the left. Okay, we're not looking at A right now. And then when we're looking at A, we're not looking at B. Okay?
Okay, sir.
All right. Achha. Then you will come across questions which use the term light inextensible string. Okay, and what happens is that you have a beam, and from this beam you have two different strings, okay, supporting an object. Okay, supporting an object with a certain mass like this. Okay, now what happens? Now the tension gets divided. If there was just one rope due to which this object was hanging, then all the weight would have been transmitted in the form of tension to that wire. But because over here you have two different strings or two different ropes, then what happens? Then the tension gets divided. Not necessarily equally, okay? Then what happens is, this is T1 and this is T2, okay? And remember, T1 is not equal to T2, okay? They will be equal unless the triangle is an isosceles triangle. And where is the weight acting? The weight is still acting downwards. Weight will always act downwards. Now, in this case, yes, the block is fixed. In this case, what we do is, we first find out if it is in equilibrium. If it is in equilibrium, we first find out the vertical components of both the tensions, and then we add the two and we equate that to the vertical component which is acting downwards. Okay. Achha, if this block is fixed, then why are tensions different? That's because you have two light inextensible strings. Okay, because you have two different strings, that's why the tension is different. If let's say you have the same string, in that case the tension is the same. But if you have two light inextensible strings, then the tension in both the strings is different. Okay. Achha, now let me answer your question. So in every case, when there is a single rope attached to two objects of different masses, so if you have a single string, okay, the tension is going to be the same throughout. We'll write this down. Okay, don't worry, we'll write this down. We'll write down these key points, that when it's the same, when it's the different, or when it's different. But remember that even if let's say you have two different strings, but if the triangle is an isosceles triangle, then tension will be the same. If however you have the same string, okay, then doesn't matter what the angle is, the tension will be the same throughout. If you have two different strings and they're making two different angles, then the tensions will be different as well. Okay, like for example over here, we have, let's say, two different angles over here. Let's call one alpha and let's call the other beta. If alpha is not equal to beta, then T1 is not equal to T2. Okay, but if they are equal, then the two tensions are also equal. All right. Okay, now let's do an example. Let's say the question says two light inextensible strings are connected with particle A. Okay, I'll draw the diagram as well. Two light inextensible strings are connected with particle A of mass m kg, held in a state of equilibrium. Okay, now let's see what that looks like. So very similar to what we've done above, but here we will also learn how to break it down. Okay, so this is your horizontal beam, and from this beam you have two light inextensible strings. Okay, and this is not drawn to scale, keep that in mind. And these two light inextensible strings are supporting an object called A, particle called A. Okay, now let's call the tension in one string T1. Let's call the tension in the other string T2. Okay, and let's imagine there to be a horizontal line in between. Okay, and the angle is alpha and beta respectively. Okay, let's call this point P, let's call this point Q. Okay, now how do we resolve the forces? That's what we're going to find out. Okay, we're going to find out how do we resolve the forces, and maybe after resolving, you may be asked to find out maybe the tension in one string, maybe the mass of the object, or maybe the tension of the other string. Okay, depending on what's given and depending on what you're asked to do. Okay, okay, now first of all, here's what we're going to do. Let's extend this line a little. Then what happens? What kind of a triangle are we looking at? We're looking at a 90-degree triangle. Okay. Now here's what we're going to do. T1 becomes the hypotenuse, okay, and this length from this point, let's call this point X, from point X to point Q becomes the opposite side. So what will be the horizontal component of T1? The horizontal component of T1 will be T1 sine alpha. Okay, the horizontal component of T1 will be T1 sine alpha. Just like that, can you tell me the horizontal component of T2? What will be the horizontal component of T2? Question for you guys.
T2 cos, T2 sine alpha.
T2 sine beta. Yes, T2 sine beta. Okay. Now both these particles will also have vertical components. Okay. Both these tensions, sorry. Now let's find out the vertical component due to T1. Since this is the adjacent side, this is going to be T1 cos alpha, and since this is also the adjacent side, this is going to be T2 cos beta. Okay. Now the question said that this is held in a state of equilibrium. Where will be the weight acting? The weight must be acting downwards. That means W equals to mg. Okay. Now because they're in equilibrium, that means that the leftward forces are equal to the rightward forces and the upward forces are equal to the downward forces. Now which two forces are acting upwards? Question for you guys. So how do you know the direction of the components, and what if Px is negative? Okay, good question. Dekho. So first of all, before you answer that question, let's answer your question. This is held in a state of equilibrium. Okay, this is held in a state of equilibrium. So what are we using over here? We're using the head to tail rule. Okay, how do we determine the direction? We determine the direction using the head to tail rule. First of all, this weight must be acting what? This weight must be acting downwards. Okay, so here you have a weight which is acting downwards. Okay, now this weight is attached to a string. Okay, this weight is attached to a string, and there must be some tension in the string. Correct? Now what do we know about tension? We know that tension always acts away from the object. Okay, so the weight is acting downwards, the tension is acting away from the object. Now where do you think this force must be acting? The force over here. Okay, the force on the imaginary line that I have drawn. Upwards or downwards? What do you think? Upwards. That's correct. Okay, now using the head to tail rule, if I join these 2 points, where do you think the force must be acting on this line? Rightwards or leftwards? Is it possible that the force is acting leftwards? Is this possible? Does this make sense? No, it doesn't. It's got to be rightwards. Okay, using the head to tail rule. Okay, that's how we know it's acting rightwards. And the same way, we know that it's going to be acting leftwards over here. Okay, because this force is acting upwards. This force is the resultant force, you can say. So this force must be acting towards the left. That's how we make the head to tail rule. Okay, does that answer your question? Okay, now because it's held in a state of equilibrium, what does that mean? That means all the forces that are acting upwards must be equal to all the forces that are acting downwards. How many forces do we have that are acting upwards? We have T1 cos alpha plus T2 cos beta. These are the 2 forces that are acting upwards. These 2 forces must be equal to the weight of the object which is acting downwards. So this is equation number 1. And then how many forces do we have that are acting horizontally? Just 2. One is acting towards the right, the other is acting towards the left. So what does that mean? That means all the forces that are acting rightwards must be equal to all the forces that are acting towards the left. And what does that mean? That means T1 sine alpha is equals to T2 sine beta. And then what do? Then we solve the 2 equations simultaneously. Now here, since we don't have any values, we obviously can't solve these 2 equations simultaneously, but this is what we do. Solve 1 and 2 simultaneously. Okay, so this was one particular case. Now take a good look at it. Let me know if you have any questions. Once we do it with actual values, you will understand how it works, but still, if you have any questions, feel free to ask.
Sir,
Yeah.
when we were doing forces in equilibrium, we considered the directions, like if it's below the horizontal, if it's on the left. So the vertical component, if it's below the horizontal, it would be negative, and if it's towards the left, it would be negative. So what about here?
So here you can do that. So for example, if let's say, another way of making this equation right here, if you focus on, let's say, this equation, since they're in equilibrium, what does that mean? The resultant must be
The same.
0. The resultant must be 0.
Yeah.
Okay.
Yeah.
So if you look at the horizontal forces, another way of forming this equation would be T1 sine alpha, positive because it's acting towards the right, plus minus T2 sine beta. Why minus? Because it's acting towards the left. And because we're talking about the resultant, this is going to be equal to what? This is going to be equal to 0. And then if you let T1 sine alpha be on this side and you take T2 sine beta across the equals to sign, what do you end up with? You end up with the exact same equation. So either you can do left equals to right, or you can do resultant equals to 0. Either way, you will get the same equation. But when you're doing left equals to right, you naturally don't consider the sign, because all the rightward forces you already have on one side, all the leftward forces you already take on the other side. But if let's say you're doing resultant of the horizontal forces to be equal to 0, then you will add all the forces taking along with their signs depending on the direction and then equate it to 0. Okay, and ultimately you will end up with the same equation. Okay, does that answer your question?
Yes, sir. Thank you.
Okay, you're welcome. Yes, Ahmed.
Sir, just a random question. Could you upload the M1 recordings according to the topic we are doing, like you did in P1? So
Okay.
it's easier to navigate through them when I want to revise. That's
I
it.
can do that. Okay.
Okay, thank you.
You're welcome. Okay, any other question? If yes, feel free to ask.
I think someone asked this question earlier as well, but मुझे थोड़ी समझ नहीं आई. So, how do we decide right or left? Like, force right किस तरफ act करिए, left किस तरफ act करिए?
Okay. देखो, I'll give you a simple hack. Now, let's say this is the point from which the object is hanging. Okay? And let's say there is a string which is acting, or which is in the direction, and the direction is slightly from this imaginary line. So if you were to compare this tension with respect to this imaginary line, where is this tension? Is it towards the right or is it towards the left?
Towards the right.
Towards the right. Okay. That means now the horizontal component of this tension will also be acting towards the right. Okay. And because the weight is always acting downwards, where will the vertical component due to this tension acting? In which direction? Upwards. Okay. Now let's say that you have another string, the tension on which is, let's call it T2. Okay. Now where is this T2 compared to this imaginary line? Is it towards the left or towards the right?
Left.
Towards the left. So where will be the horizontal component due to this tension acting? This will also be acting towards the left. ऐसे decide करते हैं. Okay?
Okay, I get it.
All right. Okay, now let's do a example question. You will notice that it's not really as difficult as you guys might think. So just a minute. It's kind of like coplanar forces. The only difference is that here you have an object with a certain mass to consider as well. Okay, so let's start with this fairly recent question, October-November 2020, paper 2, paper 4, variant 2, question number 3. Okay, let's see what it says. A block of mass m kg is held in equilibrium. Okay, keywords, held in equilibrium. Although right now all the questions that we're going to do will be in equilibrium, but just something to keep in mind. Below a horizontal ceiling, so this is the horizontal ceiling, what I was earlier referring to as the beam, same thing, by 2 strings as shown in the diagram. So how many strings do we have? We have 2 strings. So since we have 2 strings, that means the tension will be different. Okay, and you can see that tension in one string is T and tension in the other is 20. Okay, one of the strings is inclined at 45 degrees to the horizontal and the tension in this string is T Newton, so it's talking about this. The other string is inclined at 60 degrees to the horizontal and the tension in this string is 20 newtons. Find T and M. Okay, so theoretically what we're going to do over here is we are going to break down all the forces and we're going to equate the leftward forces to the rightward forces, upward forces to the downward forces. That's what we're going to do in short. Okay, so let's start. First, let's talk about the weight. What would be the force that's acting downwards? Usually it's W equals to what? W is equals to mg. Now because we don't know what m is, so we'll just call it mg only. And what's g equal to? G is equal to 10. So is it safe to say that the weight that's acting downwards is 10m? Yes or no? Is it safe to say that? Yes, that's correct. Okay, thank you. Then let's draw a vertical line over here. Okay, let's draw this vertical line over here. And now what we're going to do is we're going to break this force down into horizontal and vertical components. Okay, now let's see if you guys can get this right. Can you tell me what this angle is going to be, considering that this is a horizontal ceiling? Okay, this is a horizontal ceiling and this is a vertical line. Can you tell me what this angle is going to be? 30 degrees. Okay, how did you figure that out? This is going to be 90. 180 minus 90 minus 30 is 60. Just like that, this angle will be 45 degrees. 180 minus 90 minus 45. Okay, now what will be this component? The component of tension that's acting towards the right. This will be 20 sine 30. Okay, because it's the opposite side, it's going to be 20 sine 30. What will be the component that's acting upwards? That's going to be 20 cos 30. Yeah, somebody is saying something?
Sir?
Yeah.
So it could also be 60 cos 20, right?
It could also be 20 cos
20
60.
Cos
Yes.
60.
Now, what sine 30 and cos
Yeah.
60? They're both equal. So depending on the angle that you use, same ही answer आना. Okay, so if you take 20 sine 30 or even if you take 20 cos 60, answer same ही आना. Reason because sine 30 and cos 60 they're both equal. Okay, because of complementary angles. All right. Okay, now that you've broken down the 20 Newton force, okay, let's move on to the other force. Okay, now let's talk about the T Newton force. Now the T Newton force will also have a horizontal component. This horizontal component, however, will be acting towards the left. So let's call this is going to be T sine 45. And then this T Newton force will also have a vertical component, and this vertical component will also be acting upwards, and this will be T cos 45. Okay, once you've done this, it's as good as solving the entire question. Okay, I mean, given that you've done this correctly, you will now from this point onwards be able to solve the question correctly as well. So let me know if you have any questions so far. Okay, great. Now let's start. Because they're in equilibrium, let's start forming the equations. So how many forces do we have that are acting horizontally? Okay, listen to my question carefully. How many forces do we have that are acting horizontally? Just the two. And they're both acting in opposite direction. And because this is held in a state of equilibrium, it's safe to say that 20 sine 30, which is the force that's acting horizontally towards the right, is going to be equal to T sine 45, which is the force that's acting towards the left. Now immediately I can make T the subject and find out the value of T. So 20 sine 30 over sine 45. It's best that you keep this in exact form. So let's see what do we get. Make sure your calculator is in degree mode if let's say you've been practicing P1 or P3. So 20 sine 30 over sine 45 is equals to 10 under root 2. Okay, now let's keep it in 10 under root 2 form, in its exact form only. Any questions so far? If yes, feel free to ask. Okay. Now
So
what's
couldn't
the...
you take sorry.
Yeah.
Couldn't you take t cos 45 with 20 cos 30?
Yes, and then equate it to what?
You can equate it to like 10 meters or
Yes.
equate them to each other?
Yes.
Or
Yeah.
is that not possible?
That is what we're going to do to find the value of m. Because we have to find the value of t and m. So this equation helps us find the value of t. Now the question is that how do we find the value of m? We need another equation. So the other equation we're going to form is by using the vertical forces. Okay, so vertically you have three forces that are acting vertically. Two of them are up and one is acting down. And because it's in equilibrium, the two forces acting upwards together will be equal to the one force that's acting downwards. So t cos 45 plus 20 cos 30 equals to 10m. And now that we have the value of t, we're now going to use it to find the value of m. So 10 under root 2 cos 45 plus 20 cos 30 divided by 10. I would strongly suggest that you first make m the subject and then use your calculator and work it out as it is. Okay, so let's work this out, see what do we get. 10 under root 2 cos 45 close the bracket plus 20 cos 30 close the bracket over 10. So we get m to be equal to 1 plus under root 3. Now the question does not say that we have to give the exact answer. So if we give it in decimal, this is going to be 2.73 kg. And is it supposed to be in kg? Yeah, it's kg. Why is it 10m? Okay, good question. So if you have an object of mass m, okay, and you want to find out its weight. So what's weight equal to? Weight is equal to mg. What's g? G is 10. So m into 10, what does that give you? That gives you 10m. This is why it's 10m. Because the mass is m, in order to find out its weight, we multiply it by acceleration due to gravity, which is 10, and that's how you get 10m. Okay, does that answer your question? Yes, Lamar.
Yeah, sir. So is this all we have to do for 5 marks?
Yeah.
That's it?
Yeah, that's it. Why?
Wow. Okay.
Too good to be true?
Yeah, way too good.
All right. More or less, the questions are of the same difficulty level. See, if you're able to break down the forces correctly, you can solve the question correctly. But the challenge is always breaking down the forces. Acha, but they're asking the value of m, not the weight. Yeah, I agree. They're asking the value of m, not the weight. Weight is equal to 10m. That's how we find out the value of m. See, giving the value of weight would have been us giving what 10m is equal to, because that's what weight is. But we haven't done that. We have given the value of m. Notice that we equated it to the weight, which is 10m. Then we made m the subject. That's how we got the value of m. Okay. Scam लग रहा है. अच्छा, चलें. देखते हैं. Okay, here's another question. Don't just immediately form an opinion that, this is how it's always going to be. Yes, there are challenging questions, but having said that, the concepts remain the same. Breaking down the forces, finding out what forces are acting horizontally, vertically, whatever, forming two equations, and then getting your answer. 2 or however many equations necessary. Okay, so let's do this question. This one is slightly more challenging, and let's see what you guys have to say about this. So let's read the question. A particle P of mass 0.3 kg, that's right here, is held in equilibrium above a horizontal plane by a force of magnitude 5 Newton acting vertically upwards. So now you have an external force of 5 Newton acting upwards. Why am I calling this an external force? Because here there was no external force. It was the force that was the weight of the particle and then the two tensions, and that's it. There was no other force. Here you will have the two tensions, along with that you will have the weight, and you will have this 5 Newton force extra as well. Okay, so how do we deal with it? No big deal. Okay, let's see. So let's read the question again. A particle P of mass 0.3 kg is held in equilibrium above a horizontal plane by a force of magnitude 5 Newton acting vertically upwards. The particle is attached to two strings PA and PB of lengths 0.9 and 1.2 meters. Okay, respectively. The points A and B lie on the plane and angle APB is 90 degrees. See diagram. Find the tension in each of the strings. Okay. Now, first of all, let's call this T1 and let's call this T2. Okay, then since we have to break down T1 and T2 into horizontal and vertical components, we will have to draw an imaginary vertical line over here. Okay, Acha. Up the question is in order to break a force down into horizontal and vertical components, what do we need? We need an angle other than the 90 degree angle. Now the question is, how do we find the angle? The question is, if let's say I want to find out this angle, how do I find it? Yes, using trigonometric ratios. Now one thing that you can do is you can immediately find out the hypotenuse length. Okay, how can I find out the hypotenuse length? I'm talking about AB, by the way. AB squared equals 0.9 squared plus 1.2 squared. Okay, so AB equals to 0.9 squared plus 1.2 squared, 0.9 squared plus 1.2 squared, 2.25 square root of which is 1.5. So AB is 1.5 meters. Okay, so that means this length right here is 1.5. Okay, why are we finding AB? All right, just a minute. Let's call this angle to be alpha. Okay, just a minute. I'll explain why I found AB. I'll let AB be here as it is, and let's call this beta. Okay, in terms of alpha and beta. Okay, remember, in terms of alpha and beta, tell me what will be the vertical component? What will be the vertical component of T1? Question for you guys. What will be the vertical component of T1, considering that it's the opposite side and we have the hypotenuse side? Yes, so the vertical component of T1 is going to be this. अच्छा अब एक काम करते हैं. देखो, when things get complicated, when you have a lot of forces, here's how you're supposed to deal with them. T1, okay, make a heading of T1 and then write down the horizontal and vertical components of T1 along with their direction. Okay, so T1 has one force which is acting vertically. Okay, now we'll determine the direction in a minute. Okay, we'll see whether it's acting upwards or downwards. So the horizontal component, the vertical component is going to be T1 sine alpha. Okay, T1 sine alpha or T1 sine A also. In fact, you know what? Let's call it sine A. Since we already have a letter A, so let's call it T1 sine A, and no need to call this beta. Let's leave it here. Let's erase that. Let's not add too many unknowns to make our life more difficult than it already is. Let's call it A only. So T1 sine A is going to be the vertical component. Okay, now tell me the direction. In which direction do you think? Keeping in mind that this is held in equilibrium, where do you think this must be acting? Do you think this will be acting upwards or downwards? This will be acting downwards. Now, how do I know it's acting downwards? Here's how I know. First of all, if you can't determine directly the direction of this force, determine the direction of this force. Okay, from, let's call this X, from X to B. Because the string is on the left side of this imaginary vertical line, that means this force must be acting towards the left as well. So if this is acting towards the left, that means due to head to tail rule, this must be acting downwards. Okay, so now T1 sine A is a force that's acting downwards. Okay, now let's talk about the force of T1 that's acting. So how do you know the strings are downwards and not? Okay. How do you know the strings are downwards and not upwards? Okay, good question. Let me erase this. How do I know that the strings are downwards and not upwards? What do we know about tension? What's the first rule of tension? Where does tension act? I'll give you two options. Towards the particle, away from the particle. Is it raining at my side? I don't think so. I don't have a window in this room, sadly. I don't know. It may be. It acts away from the particle. Okay, where is the particle? Here's the particle. Okay, which direction will be away from the particle? This direction. Okay, so this is where T1 is acting, and then this is where T2 must be acting. Okay, away from the particle. All right, does that answer your question, Saad? Okay. Then what about this component? This component must be acting towards the left. This component must be acting towards the right. Now both the vertical components of both the tensions, they must be acting where? They must be acting downwards. Okay. Acha. So T1 sine A is the component that's acting downwards. Then let's talk about the horizontal component of the same force. The horizontal component of the same force is going to be T1. Because it's the adjacent side, remember this is the angle that we're using. Because it's the adjacent side, it's going to be T1 cos A, and this must be acting towards the left. Sir, the weather in Lahore is so romantic. Okay, I'm not in Lahore, I'm in Karachi. It was raining here yesterday, by the way, but not today. Okay, now let's talk about T2. Okay, now we're talking about T2. So for T2, the angle that we're considering is the angle over here, angle B. Now what will be the vertical component of T2? The vertical component of T2 is going to be T2 sine B. Okay, T2 sine B will be the vertical component. What about and where will this be acting? This will be acting downwards. What about the horizontal component? The horizontal component would be T2 cos B. And where will this be acting? This will be acting towards the right. Okay, now I know this is getting complicated, so let's pause here and let me know if you guys have any questions. Okay, now, how do we find out sine A, sine B, cos A, cos B? Question for you guys. How do we find out sine A, sine B, cos A, cos B?
Sir, can we use the A over sin A is equal to B over sin B wala rule isme?
Sine rule? Yeah, we could do that.
Yes.
We could do that, but there's an easier way. There's an easier way. We know this length to be 0.9, we know this length to be 1.2, and we worked out this length to be 1.5, didn't we? This is A, this is B, this is B. If I want to find out sine A, yeah, bolo.
Wouldn't P would be -5 since for opposite to tension?
Yeah.
PX sir, PX. जो आपने like red line draw किया, dotted red line.
Yeah.
Would it be -5?
Why would it be -5?
But since it's opposite to the tension, so it would be weight. Weight or
Okay,
tension?
नहीं अभी मैंने weight को नहीं consider किया. अभी I haven't considered the weight just yet. Okay, all I've done is I've broken down T1 and T2. Okay.
Okay.
See, weight and this force, these forces are acting vertically anyway, so we don't have to break them down. Okay, what we have to do is the tricky part is breaking down the two forces, so that's what we're focused on right now. Okay, इनको तो हम देख लेंगे, अगर ऊपर act करी होगी तो we'll add, if it's acting downwards so we'll subtract. Okay, so we don't have to worry about these two forces because we don't have to break them down. They're already acting either vertically, either upwards or downwards. Okay, now how do we find out sine A? If we have a 90-degree triangle, can we find out sine A? What's sine A going to be equal to? It's going to be equal to opposite over hypotenuse. So what's the opposite length? The opposite length is 1.2. What's the hypotenuse length? Is 1.5. So that means now we have sine A, and we're not going to use it as 1.2 over 1.5. Let's simplify this so we get 4 upon 5. Okay. Now quickly, can you tell me what sine B is going to be equal to? In fact, before you tell me sine B, tell me what cos A is going to be equal to. Tell me what cos A is going to be equal to. (0.9 over 1.5), that's correct, which if you simplify 0.9 divided by 1.5, that gives you 3 over 5. Okay, now just like that, let's find out sine B and cos B. Okay, so sine B निकालने के लिए, what are we going to do? I don't get how you're finding the angles. Okay, I'll explain this again. देखो, so basically, first of all, notice that we have to use sine A and sine B. Now, here's what we can do. We can either find out angle A and then substitute angle A, or what I recommend is that you find out sine A as it is. Okay, and you find out sine B and cos B, whatever it is that you have to do as it is. Okay, so for that, we're going to be using this triangle, but we're only going to be using the lengths. Okay, I'll ignore everything else and I'll just redraw this triangle focusing on the lengths. Okay, so I can find out angle A. Yes, that's correct, but I don't recommend that. I recommend taking sine A as it is. Why? Because if you find out the angle, then you will have to round it off correct to one decimal place, or maybe you'll have to take, let's say, 3-4 significant figures, but that will make things complicated. Okay, so instead what we're doing is this. We know this is 90 degrees, we know this is A, we know this is B. Finding out sine A means basically finding out the length opposite to A, which is 1.2, and dividing it by the length, the hypotenuse length, which is 1.5. And this length is 0.9. That's what we're doing. So sine A is equals to 1.2 over 1.5, which is equal to what? Which is equal to 3 upon 4. So what's sine A equal to? Sine A is equals to 3 upon 4. Just like that, if you find out cos A will be equal to the adjacent length, which is 0.9, divided by the hypotenuse length, which is 1.5. That's going to be equal to 3 over 5. Achha, wait a minute. This is not 3 over 4. This is actually 4 over 5. Yeah, sorry, this is 4 over 5. Cos A will be equal to 3 over 5. Okay, so let's write this down separately. Cos A is equals to 3 over 5. And then just like that, let's find out sine B. Now, do keep in mind, we have to, dekho, we can take the inverse and find B, but then we will have to plug in that angle again in sine. So if, let's say, I find A, here I will have to plug in A again. So instead of finding out A, what I'm going to do is I'm going to keep sine A as it is. So here, now when I'm forming equations, I'll just replace sine A with 4 upon 5. Instead of finding out the angle and then plugging in that angle, I'll simply replace sine A with 4 upon 5. Okay, do you understand? If you don't understand the benefit of doing this, then there's no point in doing it. Okay, so make sure that you...
explain this part again.
Okay, I'll explain this part again. Dekho. What's this? This is T1 sine A. I can find out angle A and plug it in over here. Correct?
Yes, sir.
But how about, instead of doing that, I find out the exact value of sine A and then replace sine A with whatever that is equal to. So sine A is equal to 4 upon 5. Now, instead of finding out A and then plugging in the angle over here, which means dealing with decimals, instead what I can do is I can find out the exact ratio of sine A and replace it with whatever it is over here in this equation. That's what I'm doing. That's the benefit of doing this.
Okay, sir.
Okay. Now, how about sine B? If I want to find out sine B, that's going to be opposite over hypotenuse. That means 0.9 over 1.5, which is going to be equal to 3 upon 5. So let's write this down over here. Sine B is equals to 3 upon 5. And then just like that, cos B is equals to adjacent over hypotenuse, which means 1.2 divided by 1.5, which is going to be equal to 4 upon 5. So let's write this down separately. Cos B is equals to 4 upon 5. Ab dekho what happens. Sir, let's say my final answer turns out to be 59.4. Yes, you will lose a mark. Reason because CAO means what? CAO means correct answer only. Okay, so when something can be done in exact form, it's best that you do it in exact form only. Okay, now we've done all the hard work. Okay, now notice everything will fall into place. Achha, before that happens, let's talk about the other forces that we have acting on this particle. What are the other forces? You have the 5 Newton force, which is acting upwards. And then what about the force that's acting downwards? That's the weight. And what will be the weight, considering that the mass is 0.3 kg? What will be the weight? Simple question. What's 3 newtons? Okay, 3 newtons. And where is this acting? This is acting downwards. Okay. Now remember, all this is held in equilibrium. Now because all this is held in equilibrium, that means the upward forces will be equal to the downward forces, the leftward forces will be equal to the rightward forces. Okay, now let's first talk about the leftward and the rightward forces, okay, because there aren't too many horizontal forces. So this force is acting towards the right, T2 cos B is going to be equal to T1 cos A. So this is our first equation right here. Now the benefit of finding out cos B and cos A and sine B as it is that I can, instead of plugging in the value of B over here, the angle, and dealing with a lot of decimals, what I can do is I can easily replace cos B with 4 upon 5. That means T2 multiplied by 4 upon 5, and just like that I can replace cos A with 3 upon 5. That means into 3 upon 5. Okay, now do you guys see the benefit? So we can cross out the 5's. We have 4 times of T2, which is equal to 3 times of T1. This is one equation. We'll leave this over here for now. But yeah, this is the equation. And let me know if you have any questions so far before we form another equation. Okay, great. Now let's talk about all the upward forces and let's equate them to all the downward forces. How many forces do we have that are acting upwards? Just this force. Just the 5 Newton force is the force that's acting upwards. All the other forces are acting downwards. So that means 5 equals to T1 sine A plus T2 sine B plus 3 newtons. Okay, so let's double check and see what we have done. Let's make sense of it. The upward force, the 5 Newton force, okay, and all the other forces acting downwards. So 5 equals to T1 sine A plus T2 sine B plus 3. Okay, now we have sine A as it is, so T1 multiplied by 4 upon 5 plus T2 multiplied by sine B as it is, that's 3 upon 5, and then plus 3. Okay, so this will require a decent amount of simplification. First of all, 5 minus 3 kar that's going to be 2. So 2 equals to 4 upon 5 T1 plus 3 upon 5 T2. Okay, and this is our second equation. Now take a good look at this equation and tell me if you have any questions. And we're almost there, by the way. Okay, what do we do now? Now we solve the two simultaneously. Okay, now you can make either T1 the subject, or it's up to you however way you want to solve them. Either you want to use substitution or you want to use elimination. It's entirely up to you. So if, let's say, I make T1 the subject, that's going to be my third equation. So T1 is going to be equal to 4 upon 3 T2. Okay, this is my third equation, and since this has come with the help of the first equation, we will substitute it back into the second equation. So 2 equals to 4 upon 5 into 4 upon 3 T2 plus 3 upon 5 T2. Let's see what do we get. So 2 is equals to 16 upon 15 T2 plus 3 upon 5 T2. Now skip some working over here. 16 upon 15 plus 3 upon 5. 3 divided by the answer. So we get the value of T2, and the value of T2 is 2 divided by the answer, sorry. 16 upon 15 plus 3 upon 5 and 2 divided by the answer. So we get T2 to be equal to 1.2 newtons. Okay, now that you have T2, in order to find out T1, here's what we're going to do. I'll continue from here. T1 is equals to 4 upon 3 T2. Plug in the value of T2. So 4 upon 3 multiplied by 1.2. And then you find out the value of T1. 4 divided by 3 into 1.2. And that's equal to 1.6 newtons. And there you go. This was, although the number of marks were the same, but this was a challenging one, because you had to first find out the angles. Now, can you repeat from the third equation? Okay, so basically, if you've understood how I got the first and the second equation, from that point onwards, we're just solving these two equations. You can think of T1 as x, and you can think of T2 as y, and we're just solving the two simultaneously. That's what we're doing. It's like 4x equals to 3y, and 2 is equals to 4 upon 5x plus 3 upon 5y. That's what we're doing. So I made T1 the subject, substituted T1 in the second equation, solved, got the answer. That's what I did. Okay?
Sir, in the second equation couldn't.
Yeah, go ahead.
Sir, in the second equation, why didn't you multiply 2 with 5 to get 10 is equals to 4t1 plus 3t2?
Yeah, now that I think about it, that would have been a better way to solve it. It just didn't occur to me. But yeah, that way we would have avoided dealing with fractions and we could have solved it that way. Okay, you're right. We could have done that. Answer would have been the same. Okay?
Okay.
Alright, now I am going to give you guys a question to solve now. Here it is. It's a 6-mark question. We have more than 15 minutes, enough time for you guys to solve. It will be lengthy, okay, but this is not that difficult. So you can add questions from 2023 worksheets to, I think the worksheets are updated to, yeah, okay, I'll do that. 2023, they're not. Are you talking about the worksheets of kinematics and coplanar forces that I've shared? Is that what you're talking about? Okay, yeah, I'll do that.
Will this be included in the test?
No, this is not. These are not coplanar forces. This will not be included in the test. Okay, so I'm going to solve this now. I will write down the answer here just in case. The answer for T is 107 newtons and the answer for theta is 37.5 degrees. Okay? Okay, now. So let's start with the 120 Newton force. Okay, let's break down the 120 Newton force. So quickly, tell me the vertical component of the 120 Newton force. Question for you guys. What will be the one vertical component of the 120 Newton force?
120 sine 45.
120 sine 45. And where will this be acting? This must be acting upwards. Now quickly tell me the horizontal component of the 120 Newton force. What will this be?
120 cos 45.
120 cos 45, that's correct. And where will this be acting? This will be acting horizontal, towards the left. Okay, then we have the T Newton force, okay, which needs to be broken down. So what will be the vertical component of the T Newton force? Question for you guys.
T sine theta.
T sine theta. What will be the, and this will be acting upwards as well. Where will be the what will be the horizontal component of the T Newton force?
T cos theta.
T cos theta, and this must be acting towards the right. Okay, and then don't forget that you have another force of, which is the weight, and that's the 150 Newton force, and weight being weight always acts downwards. Okay, now once you've done this, then what you have to do is you have to recall that this is hanging in equilibrium. That means left equals to right, up equals to down. So let's start with left equals to right because there aren't too many for horizontal forces. So the one that's acting leftwards, it's 120 cos 45. The one that's acting rightwards is T cos theta. Now, if you want, you can make T the subject. If you don't do that, that may be perfectly all right. Okay, maybe we'll have to do it in the next step eventually. So 120 cos 45, that's something we can simplify, and that's 60 under root 2. 60 under root 2 is equals to T cos theta. Now, here we have two unknowns, so clearly this equation is not enough. Okay. Now let's talk about the other equation. The other equation where all the upward forces, that is 120 sine 45 plus T sine theta is equal to 150 newtons. Okay, up equals to down. So here also we can do a bit of simplification. We can make T sine theta the subject, just like we made T cos theta the subject, and that's going to be equal to 150 minus 120 sine 45. Now, if and only if we get an exact answer after doing 150 minus 120 sine 45, will I write it? Okay, I don't. Since we're getting it in 65 point something, we'll let it be as it is. Okay. Now, what can I do? I can make T the subject. If I do that, T is equals to 60 under root 2 upon cos theta. And since this is the third equation, which has come with the help of the first equation, where do we plug it in? We plug it into the second equation. So 60 under root 2 upon cos theta into sine theta is equal to 150 minus 120 sine 45. Do you see where this is going? We have sine theta over cos theta. What is that going to be equal to? Tan theta. That's correct. Always be mentally prepared to have this identity every time you're resolving forces. Okay. So 60 under root 2 tan theta is equals to 150 minus 120 sine 45. Okay, I just made an error, wrote 40 instead of 45. So just be careful there. Tan theta is equal to 150 minus 120 sine 45. Okay, divided by 60 under root 2. Now this is what I meant, that you should keep everything in exact form till you get the final answer. Now I can use this equation to find out the value of theta. 150 minus 120 sine 45 divided by 60 under root 2. Take tan inverse of the answer, make sure your calculator is in degree mode, and you get the value of theta to be 37.5 degrees. Once you have theta, you can find out t. That's going to be 60 under root 2 over cos of the answer. Make sure you use your answer key. So t is equals to 60 under root 2 over cos of the answer. And what do we get? We get 106.977, which if you round off correct to three significant figures, which you have to, it's going to be 107 newtons. First, I did try it without exact values. Yeah, see, that's the problem. If you round off within the same part, that's when you're in trouble. So if, let's say, you're using one value of the previous part in order to solve the next part, then you can use the rounded off value. But within the same part, especially when you have questions like these, it's best to keep things in exact form. And that's the same reason why here we figured out the exact values of sine A, sine B, cos A, cos B, instead of finding out the angles. Okay? Now, take a good look at my solution and let me know if you have any questions. I will give you guys some homework. I'll filter out some questions which don't involve friction and all that. And you guys will have to do those only. Okay, so I'll stop here. See you guys inshallah in the next class. Take care everyone. Allah Hafiz.